Okay, so there's one little thing I want to go over that I don't think we went over enough, and then we're going to get into some new stuff. Oh, let's just do this. Let's do, if I had the square root of, let's do, yeah. Let's do something a little more obvious. Sure. Okay. How would you do this? Square root of 44. Is the square root of 44 22? How do you show somebody it's not 22? You just say what? What's the square root of 9? Why? Because 3 times 3 is 9. So show somebody square root of 44 is not 22. What would you say? 22 times 22 ain't 44. Creates a person. All right, I like it. How do I do this then? I can't do the square root of 44 directly. What do I do?
11 to 4 maybe?
Yeah. Break it down. So I got a part I can do. So then what do I? And then I do it. And a part I can't do. So it just sits there. Square root of 4 is 2. Square root of 11 is? I don't know. All right, now watch. This is the connection to make between numbers and letters. Square root's not going to work on a cube well, is it? But doesn't a cubed have something in it that the square root can do something to? There's an extra, how many extra a's are in there? How many extra a's? Do you see what I mean? What extra number is in here? 11. Because 11 times the 4 I can do, the 11 I can't. How many extra a's are in here? 1. So how do I do this? I break it up. What's the square root of a squared? Yeah, let's assume we don't need absolute values, right? Some of the homework says assume the insides aren't negative. Okay, cool. So let's not worry about absolute values. And then this is just square root of a. It just stays there. Same way that square root of 11 had to stay there. They are very similar. Now, but I showed you this. But I want to make sure you really see why this is true. The shortcut here, what's the root? 2. 2 goes into 3 once with 2 goes into 3 once with 1 left over. So watch. If I had the 7th root of m to the 19th power, 7 goes into 19 twice with 5 left over. I love this shit. Why exactly does this work? You can either break this up into 7th root of m14 times 7th root of m5, right? 7 goes into 14. You guys with me? And that's where m squared and 7th root of m5 comes from. Yes?
Oh, I was just going to say, we had this kind of problems in the homework too.
Exactly. Yes. So I wasn't too concerned. Nobody asked questions, so you guys all obviously understood it. But I just want to make sure you really see why this is true. Another way to look at this is, what is this? M to the what? Change this into a fractional power. M to the 19 over 7. Make that a mixed number. And listen to yourself. Make it a mixed number. 7 goes into 19 twice with 5 left over. See how it's the same language I just used here? So there's a whole m squared and then an m to the 5/7. So the best short, 7 goes into 19 twice with 5 left inside. Right? The way you've said it ever since you first learned it is the way it works with roots. You gotta love that. You actually have to love that. It's California law. Montana, you don't have to. Montana, different people. Okay. Maybe. So if I had, for example, 5th root of a to the 8th, c to the 11th, d to the 21st. 5 goes into 8 once with 3 left over. A's are done. 5 goes into 11 twice with 1 left. 5 goes into 21 4 times with 1 left. Done. Next. Because radicals are fractional powers, that's why that type of shortcut works. It's such a beautiful shortcut. So some of you guys might be like, well, why don't stupid frickin' numbers work that way, freaking Jeff? What the shit? They do. Anybody know how many 2's make 32? Have you guys figured it out as you're doing your work? How many 2's make 32? 2 times, 2 times. Nope, 1 too many. 5. So if I write this as square root of 2 to the 5th, 2 goes into 5, right? So 2 right here, right? 2 goes into 5. 2 goes into 5 twice with 1 left over. Help me. 2 goes into 4 twice, and then there's an extra one, right? You with me? How would I do square root of 32 more directly? Square root of 32 is square root of 16 times square root of 2 is 4 square root of 2. Well, what do I get here? 4 freaking square root of 2. I really, listen. Why does math do different shit to numbers and letters? Because they're not written in the same format. If I wrote a number in the format that I see letters, how do I normally see letters? A cubed e to the 21st. How do you see numbers? 32. So of course they're not going to look like they work the same way. But if I write it in the same format, they work exactly the same. They have to. Because all these are numbers I don't know yet. So they have to work the same thing that numbers do. Do you guys kind of see what I'm saying? A little bit. This is the hard, scary, painful part, where you actually have to see why things work the way they do. If you get there, math is easy. Okay. Getting there is the hard part, I understand. All right. So that's the one little thing I wanted to make sure was a little bit tightened up. I didn't really put a problem like that on the test because I figured we needed to tighten that up a little bit. So we essentially left off right at 10.4. I did put a problem on the test that dealt with things dividing, because if they have the same root, you just reduce. So there's that one problem with like something over the root of 10 something. Whew, you guys really made that one harder than I intended. What's this? What's the cube root of 4 times the cube root of 7? Cube root of 28. Why are you allowed to do that? Same root. So what is the 5th root of what you got? I don't know. 90 divided by the 5th root of 9.
10.
5th root of 10. I mean, which is not 2. That's not 5 into 10. Do you guys? So if it's the same root, and it's the way it's always been. What's 8 divided by 2?
4.
Why are you allowed to do that? Because they're both the same root. Namely, not really no root, right? So all we're saying now, if there's a root, it better be the same, or else you can't do it. I like it. But here's the new thing in section 10.4. There's something called rationalizing. Somebody know what the word rationalize normally means? Like psychologically? If you rationalize something. Rationalize something is like, if you go through a red light and you're like, it was okay for me to do that because I'm really late, and if I get there late, then this bad thing is going to happen. So you just rationalized why it was okay for you to break the law, right? We do that kind of thing all the time. It was okay I did that because I got to do this, and this person relies on me, and I got to do this. That's kind of one example of rationalization. In math, it's not that. Here's what rationalization is in math. What's a rational number in math? Rational number. The hell does that mean? What's the root word of rational?
Ratio.
Ratio. So what's a rational number? And what's ratio mean? What kind of number has a ratio in it? A fraction. I love it. So rational numbers are things that can be written as fractions. So the most common example of something that is not rational is square roots. That is not rational. Square root of 7 is some ugly decimal that never ends and has no pattern to it. Does this sound familiar at all? Rational numbers, they have to be written as fractions, or they are terminating decimals, or they're decimals that have a pattern to them. Roots, if you can't do them, they are disgusting. Personally, I think they're beautiful, but they're just these numbers, these decimals that never end and don't have a pattern to them, like pi. Okay, so they are irrational. So if I say I want to rationalize something, the most immediate thing that could mean is I want to get rid of the root on something. So for example, if I want to rationalize the denominator on this, let's see. You see how the bottom is very irrational. What's the cube root of 2? Can somebody take a guess? What's the cube root of 2? It's got to be bigger than 1.
1.5.
Yeah, 1 point something would be a decent guess for any human, right? We're like, I'm not a calculator. 1 point something. All right, I love it. It makes sense. So that bottom is gross. Now, help me out. Oh, I should do this. A little side note. So you agree with me, the bottom is totally irrational, right? You guys with me? Is the bottom of this one irrational? Why not?
Because you can cube it for
Because I could do the cube root of 27. So what's really on the bottom there?
3.
That's totally rational. It's all good. The bottom's totally rational. No worries. Here, no good. Why can't I do this, but I could do this? Why can't I do this one? Why was I able to do this one? Why is the answer 3? Why is the answer 3? Because 27 has 3 3s in it. Now, stay with me. This is awesome. I don't like calling this rationalizing the denominator. I like calling it completing the root. What does this root need in it? How many things? 3 things, because it's a cube root. So why could you do the cube root of 27? Because 27 has 3 times 3 times 3. It's got 3 3s, so it's doable. Are you guys with me? That's one of the better ways to look at radicals in general, is that's what it's asking you. What does it take this many up to make this? So what do you have to have inside? This many somethings. So how many more 2's do I need? So I can do the bottom. 2 more 2's. What did we just say? What is it? How many does it need inside? 3. How many do I currently have? 1. So how many more 2's do I need? 2 more. How many 2's are in here? 1. How many things does it need? 3. So how many more 2's does it need? 2 more. And what am I allowed to do with any fraction? I can multiply the top and bottom by anything except 0. So I want to give it 2 more 2's. Oh, my poor little black marker, you're dead. If I do this, though, why won't this work? If I just do that, why won't that work? That's got a cube root. This has nothing. This little piggy head roast me. So I have to do this. Now please let that be not that bad. Do you see how the root's of 3? And then you say, well, how many things do I have in it currently? 1. So it needs 2 more of those things. You can't do something to the bottom and not to the top. That's not legal. What do you got on the top? I get shit. But I don't care about the top, do I? I'm trying to make the bottom nice. Yes, sir.
So does the 2 cancel?
No. How do you mean cancel?
Like outside the 3, the cube, and the 2 squared?
What's the cube root of 2 times the cube root of 2 squared? Cube root of 8. And what's the cube root of 8? 2. There you go. Do you see how this is a third of a 2? Do you guys see what I mean? This is a third of a 2. What is this? Cube root of 2 is 2 to the... Cube root of 2 is 2 to the 1/3 power. We know this. A radical is a fractional power. Why does that make sense? Because it cuts it in that many parts. So this is 1/3 of a 2. Are you guys with me? If I give it another 2/3 of a 2, what did I just make? A whole freaking 2. In fact, did I look at it that way to do this problem? No. I very technically did this. I gave it 2 more 2. That's 8, and the cube root of 8 is 2. But look at another way you can look at it. It's 1/3 of a 2. If you give it 2/3 of a 2, I made a whole 2. Aw. But again, do you have to look at it that way? No. I like to call it complete the root. If that would have been a 5th root, I would have multiplied by how many more 2's? 4 more 2's. It would have been 2 to the 4th there. Was there much thought involved in what I just did? No. Right? That's why I call it complete the root. Give the root what it needs. Why is the bottom not doable? I don't have enough stuff in here. All right, let me pack some more shit in there. And then I can do it. That's the idea. Let's do another one. That's got to equal. Oh well. So I know whatever I multiply by, same instructions here. It's got to be in the 7th root so that it actually can get in there and do stuff, right? And then you just say to yourself, okay, I've got 2 A's, so how many more A's do I need? 5 more A's, because it's the 7th root. And how many more B's do I need? 2. So on the top, I get 7 times the 7th root of A5 over B, times B squared. On the bottom, some of you guys might realize I'm going to get AB. I just made a whole A and a whole B, but if you look at the work, you get 7th root of A7, B7. What's the 7th root of A7, B7? Say again? It's the 7th root. What does the 7th root do to something? Cuts it down, right? What is the 7th root of A to the 7th?
What?
A to the 1st, right? So what happens? They kill each other. 7th root and the 7th power are opposite operations. They will kill each other. So I just get on the bottom AB. We've known this for a while. What's the cube root of W to the 6th? You know what happens. What's the cube root of W to 6?
W2,
W squared.
W squared, yeah.
Right? Because 3 goes into 6 twice. Well, 7 goes into 7 once, and 7 goes into 7 once. Okay, maybe. Because what would this be? What's the 7th root of A to the 7th? That would be A to the 7 over 7 power. Well, that's A to the 1st freaking power. All right, let's do another. Let's bring some numbers into this. Huh? This is the answer. Let's see, what about... Let's not do that, sorry. Let's make it 5. Do I need 3 more 8s, or is there a better way to look at this? When you have a number, it might be hiding what it's already got. What has 8 already got in it? How many 2s?
3.
So this is really... Now I can see what I've got, so I can see what I'm missing. How many 2s am I missing? What's the root?
4.
4th root. So how many things does it need in it? 4. How many 2s does it currently have in it? So how many more 2s does it need? 1 more. See why complete the root makes more sense? For those of you paying attention. Why can't I do the 4th root of 8? Because there's not enough 2s in there. Right? It's like, what's the cube root of 9? Ah, shit, if there was only 1 more 3 in there, I could do it. That's the idea. So this is the 4th root of 8. That sucks. It's only got 3 2s in it. So let me give it what it's missing. It's missing 1, 2, and then I can do the fourth root of it. And how many A's am I missing? Yeah, exactly. So now I'll have 4 A's altogether. And then I can do the fourth root. The fourth root goes away, and the bottom becomes nice. So in mathematics, we normally do, dividing sucks in the first place. And then dividing by something that's gross is even worse. So that's why we normally rationalize the denominator. We make the bottom nicer. This is already bad in the first place. So I got to do the same thing to the top. See how the top doesn't get any choice. Whatever I do to the bottom, I must do the same thing to the top. So what do I get on the top? 10a cubed w. I like it. And on the bottom I get 4 through to 2 to the 4th times a to the 4th. So what do I really get on the bottom? 2a. On the top I get all this shit here.
Can we just do one more?
Yeah. Erhan says only one more, even if you wanted more. Okay, I like it. You guys are getting the idea. So what if I had 6th root of 7b over the 6th root, holy macaroni, of, let's say, what do you got, Jeff? 128 m cubed d 5. Sure. So first thing I would do is sort of related to something I brought up earlier. If you rewrite the number to be in the same format as the letters, you can think about them in the same way. So 128, that format sucks. 128 is twice 64, which is twice 32. 32 is 5 2s. So 128 is 7 2s. If you don't like that, you can just take 128 and break it down, break it down, break it down, break it down. You have 1, 2, 3, 4, 5, 6, 7 2s. It's a circle. So this would be 2 to the 7th. You guys cool with that? If you have a big number, you just break it down and see what it's made of. So here's the weird thing with this. Can't I do something with this? Let me look at it this way. What number here would 6 be able to go into? 6, but also what's the next number up that 6 could go into? No, I mean evenly. 6 can go into 6, 6 can go into 12. I like it. So normally, if you have a number smaller than this one, you try to make this become this. If you have a number bigger than this one, you make this become twice that, or 3 times that, whatever's the next thing. Something that it can go into nicely. So let's start with the letters here. How many more M's do I need? So I need 3 more M's. How many more D's do I need? 1 more D. Like it. And how many more 2's do I need to make this doable? To make this become 12? How many more 2's do I need to make 6 be able to go into this? 5 more 2's to make it become 12. And then I could do 6 into 12, right? So why am I making this a 6? So that 6 can go into it nicely, right? 7's already bigger than 6. Oh, shit. Okay, let me make it the next number up. What's the next number 6 goes into? 12. So let me give this guy 5 more 2's. And then you just see what happens. So this would be a 6th root of 2 to the 5th is 32 times 7. 32 times 7 is, oh gosh, I can't think. 224. So all that stuff just gets slammed together. What do you get on the bottom? I get 6th root of 2 to the 12th, m to the 6th, d to the 6th. So on the top I get this business. On the bottom, what do I get? 6 goes into 12. Twice, so 2 squared is 4. 6 goes into 6 perfectly. 6 goes into 6 perfectly. Done. I made the bottom nice. So it really is, you're allowed to multiply top and bottom of a fraction by anything you want to except 0. So you multiply it by something that will give the bottom what it's missing. So when I say rationalize the denominator, think complete the root. What's the root need? What is it missing? Let me give it to it. I like this idea because it's very similar to the way we do. Remember this stuff? What's he made of? What's he missing? Give it to him, right? That idea. It's a very similar idea. No? You guys don't remember this? You're like, don't talk about that shit. What are you talking about? I'm sorry. But I love to make large, overarching ideas. Then there's less crappily little details to remember. You can remember these large ideas that connects everything together. Okay, so that's enough of that one. So that's what they mean when they say rationalize the denominator. You just think to yourself, how many things does the root need? Let me give it what it's missing. Okay, I think that was the last. That was the only other new idea, yeah, in section 10.4. So here, all right, so we got what they want from this. More than you wanted? Okay. I love 10.5 because it's about time we saw a purpose for something like this. Remind me, how would you do square root of 28? Yeah. Square root of 4 times square root of 7. Square root of 4 is 2. Square root of 7. 2. And so this idea plus this idea. What do you think this is? Actually, let me start it this way. What's 2y plus 3y? Oh, that's amazing, right? 2 things I don't know, plus 3 of those same things is 5 of those damn things I don't know. Does that idea change? Or no, it doesn't change. So what's 2 square root of 7 plus 3 square root of 7? 5 square root of 7. Beautiful. It's the same idea. Do you know what y is? No. That was no. What is y? Is it a philosophy class now? I know y. What's the square root of 7? Tell me. I don't know. Same shit. I got 2 things I don't know, plus 3 more things I don't know. It's 5 of those damn things I don't know. That idea does not change. Okay, I like it. Oh, okay, John. So what if I add this? So now, in section 10.5, you'll see stuff like this. Square root of 28 plus the square root of 63. Now, please, dear God, are those like terms? You cannot just say this is the square root of 91. That's bullshit. I don't see any 90. What the hell? You can't just add the insides together. Right? What's 2 squared plus 3 squared? It is not 5 squared. Holy shit. Of course not, right? Because do you add first or square first?
Square.
Of course you square first. And what are radicals? What are they? What's a better way to write them as fractional powers? So radicals are actually the same place in order operations because they are powers. Right? Please excuse my dumbass, all that kind of stuff. So you cannot just add those together. That's insane. But they're not like terms. But you don't just say I can't do shit, because what are you trying to do? You try to break them down to see if maybe there's a like term hidden in there. 28 we already did. How do I do square root of 63? Yeah, 9 times 7. So we get 2 rad 7 plus 3 rad 7 is 5 rad 7. Holy shit. So I rewrote these. I saw there were these hidden like terms, and then I just put the like terms together. That is one purpose for being able to simplify a radical. Break it up. All right, let's do another one. So what about this? What if I had, what if there's a number out front? So like 5 square root of, what you got, Jeff? I don't know, 45 minus 2 square root of 20. Good. So you get 5 square root of 9 times square root of 5. Good. It's 2 square root of 4 square root of 5. And what is everything doing in this first term? They're all doing what to each other? This first term, what are they all doing? Multiplying. What is the square root of 9? 3. And then what do you do with the 5? Multiply. You don't make it 8. It's not 5 plus 3. This is 5 times this stuff. So 5 times 3. Yeah. 2 times 2. So I get 15 rad 5s minus, gather, 2, 4 rad 5s. Can I see that? 15 rad 5s minus 4 rad 5s is 11 rad 5s. So rad 5, rad 7, rad 3, they all act like variables because they're all some little thing I don't know.
What is rad stand for?
Radical, which is like the root. That's another name for the root. It's totally radical. Yes?
So it's 5, 9, and how'd you get that 5?
Which
The
one?
top, the very top.
This?
I know the other one.
That's the same 5. Or this 5?
Yeah, yeah.
What is 45? 9 times 5. Yeah. So I'm just breaking it up like I did the 28 earlier. 20, 4 times 5. I like it. All right, what about this one? I think I like blue. Blue shows up nice. Oh, what'd I do? Oh, wait. By the way, you guys can tell that's cube root, right? Not 5 cubed or something crazy. Yeah. So break this up as?
6,
No.
4, 6.
Nope. It's a cube root. 8 I can do. Times what? 3.
3.
8 times 3 is 24. What do you think?
Is it cube?
Yeah, 81's 9 times 9. 9 times 3 times 3, 27 times 3. There you go. 27 times 3. And watch this. I want you to realize something. If these are going to be like terms, what root's going to be left here? Cube root of 3, right? So what has to go into this if it's going to be doable? 3. So you just divide this by 3 and see if it goes in. Most of the time it is going to, because most of these problems are going to work. So then here I get cube root of 8 is times 2. 4 cube root of 3 plus cube root of 27 is times 5. 15 cube root of 3 is 4 of these plus 15 of these. 19 of those.
Where'd you get the Y?
Y.
4.
I gotta remember, I'm trying to make my y's like this. Okay. So here, you guys try these two. I'll give you 2 problems to try. Let's see. Start to use them all up. All right, it'll do that. See if any of you paid attention. That's a 50 there, right? How's this guy work? Yeah, 25 and 2, so you get 5 rad 2. How's this guy work? Yeah. Gather cube root. So you get square root of 49 is times 3. 5 rad 2s minus 21 rad 2s is. What's 21 minus 5? 21 minus 5. What's that? Alright. And then here, notice that 297 is disgusting as all shit. Right? But, can you do anything with this guy? No. So what has to go into this guy? 11. 297 divided by 11 is 27, which is a cube root of 11.
Sweet.
So you get 4 cube root of 11 plus cube root of 27 times cube root of 11. Do you understand? Again, you're going to have a part of the problem that's a hint. The only way there's going to be like terms is if this has an 11 left inside of it. If it doesn't, screw this problem. There's no reason to do it. So let me divide that by 11, and hey, holy shit, a part that I can do is there. Do you guys understand? So you use part of the problem as a hint as to what to do, especially when you got these ugly-ass numbers that you don't want to look at. Don't blame you. So I got 4 cube roots of 11 plus 3 cube roots of 11 is 7 cube roots of 11.
How do you know, like, on when you're factoring 98, how do you know which numbers to use?
Even on 98, I know there's going to be a 2 left here, so I can just divide this by 2. Or you start dividing the number by rootable numbers. And you'll get it very quickly. 98 divided by 4 doesn't work, by 9 doesn't work, by 16 doesn't work, but 98 divided by 49, hey, that works. That kind of takes a long ass time, right? But I'd much rather say, well, that one's going to be done. Let me divide that by 2 and see what happens. I really want you to understand. If 2 doesn't go into this number, then there's no like terms anyway. There's no point to trying to do anything. You just circle and go on. You're like, you can't simplify this. On that note, I want to show you a couple. Might as well move into the green book so I can stop trying to make stuff up on the fly.